Okay, so today we return to the most important application of the Lorentz series, which is called the residue integration. So now we're officially in section 16 and 3. Okay, so, well, we have a function. Suppose that f is analytic. Of course, f is analytic, and suppose that suppose that f has an isolated singularity. At point z0, then in this case, you must be able to find some positive number. I would say r such that f is analytic on z minus z0, analytic on this analysis of radius r, and well, the Lorentz series of this point of this function about this point should be something like this. These are the positive powers, and these are the negative powers. Z minus Z0 to the n. Okay. Okay. So this is the Lorentz series, and according to the Lorentz series, and today I want to focus on this term. So on where these negative powers of Z minus Z0 appears, and for these coefficient, and the Lorentz theorem says the theorem says that these numbers are 1/2 pi I times the integral of fz and z minus z0 minus n and plus 1. And of course, yeah, even though I will not mention here, but you will automatically assume that this guy is enclosing this point, and this is a curve contained in this analysis. And also, we will assume that this guy is positively oriented. Okay, so this is true for all positive integers. Okay, yeah. All right. And in particular, suppose that we plug in that n equals to 1 in this on here. Then, well, if you plug in n equals to over there, then this is minus 1 plus 1. So everything raised to the power of zeros. So, well, basically, you can simply ignore this denominator. So B1 is 2 pi I of C f of z and dz. Okay, so what do you know from here? Well, suppose that we are interested in the integral of my function f around this positively oriented closed curve C. And well, if you want to compute this integration, then instead of just using the brute force of computation, I mean, you can always introduce the parameterization of this curve, and you take the integration by the parameter t. But that is one option. But in this case, suppose that you are able to find the Lorentz series of your function. Then the first coefficient of this negative power of z will gonna give us the idea what your integration is. Okay. Well, it tells us, your integral of your function around this curve should be the first coefficient b1 times 2 pi times r, right? So this is basically the idea of the residue integration. Okay, so here goes the definition. Suppose that f has a, well, sorry, I should say an isolated singularity at this point, and we let b1 to be the first coefficient of the Laurent series of f about z0. Then b1 is called the residue of f at the isolated singularity and this is our notation. We write b1 is the res z at point z0 of function f of z. So this is our definition of the residue. Well, and clearly, then the integral of my function around the simply closed curve C is just 2 pi I times the residue. Okay. So I want to emphasize just two things about the residue. First, the residue only makes sense for the principal part of the Laurent expansion of your function. So what does it mean? So what is the principal part? So suppose that my function has, suppose that the Laurent expansion actually says that this is true for every analyst. So as long as f of z is analytic in this analyst. But and in this case, the negative powers of the summation is called the principal. In this case, we cannot say the negative power of this expansion is a principal part of this function at f. Why? In order to be a principal part, then you should always make sure that its inner radius equals to 0, right? If inner radius is not 0, then that cannot be called a principal part. So, and here, so therefore, in order to get the residue, then first of all, you will need to consider the Laurent expansion of your function, and also make sure that the inside radius equals to 0. Then you can get the first coefficient of the negative power, b1. Okay, so this is just one point. And and also this Laurent and this theorem, this last theorem, so the last statement also makes sense when your f doesn't have any singularity at all. Why? Because suppose then my function, this is my curve, and suppose that f is analytic everywhere in this simply connected domain enclosed by this curve C. In this case, what is the Laurent expansion of your function at this point? And in this case, we can always consider this guy to be the removable singularity. right? And in this case, there should be no negative powers in your Lorentz series. I mean, in this case, your Lorentz expansion of the function at this point it should be coincide to the Taylor series about this point, right? And in this case, B1 equals to 0. And you know what? When your curve is enclosing a simply connected area and your function is already analytic on this area, then you're pretty sure that this integral about this curve should be 0, right? So in this sense, this last statement is also true for when you don't have any singularity inside the curve, inside the region bounded by curves. Okay. All right. Okay. So and today we are going to study. So we are going to figure out how useful how useful the notion of the residue is when you're doing an integration. So let me try to evaluate this integral. Well, see, I have a function z to the fourth and dz, and C is a curve. So C is a circle of radius 1 centered at the origin, and we are assuming that this guy is positively oriented. In other words, this is counterclockwise orientation. Okay. If you do not have the residue, then well, there is no way around. So we actually need to introduce the parameterization of this curve, and we plug into here, and we try to integrate this guy by using the parameter t. So that is our brute force of computation. But anyway, so this time, we try to find the residue of this integrand. Well, of course, this guy has a isolated singularity at this point, at the origin, right? And clearly, this singularity has been enclosed by this curve C. Okay, so now to find the residue, we need to first find the Lorentz expansion of this guy. So 1 over z to the fourth, and this is from n0 to infinity. This is the power series of the exponential function, and subtracted by 1. So what is this? So this one is supposed to be from 1 to infinity, and so this is from z1 to infinity, z to the n minus fourth by n factorial. Okay, so let me write down the first few terms of this infinite series. So should be 1 over z third plus 1 over 2 factorial times 1 over z squared, maybe, yeah. And 1 over 3 factorial times 1 over z, and 1 over 4 factorial plus times z to the zeros. Okay, so I can always omit this, and 1 over 5 factorial times z to the first, and da. Okay, and well, always this is true for when z is between 0 to infinity. Okay, so can you figure out the residue out of this expansion? Yeah, clearly we can, because well, this guy is the first coefficient of the negative powers of your Lorentz expansion. So residue should be 1 over 3 factorial. In other words, 1 over 6. Okay. So the residue at this point of this guy is 1/6. Okay, so as a consequence, the integral of this function about this closed curve is just the residue times 2 pi times I, which is pi I over 3. Okay. Yeah, I believe this is way easier than just brute force of computation, right? So actually, this technique is especially useful when the Lorentz expansion is easier to find. So okay, maybe there is always some case that Lorentz expansion is very hard to find. In that case, well, residue method will not be as useful as before. But however, in this case, all the functions involved in this integrand, they are all elementary functions, right? So in this case, residue is good. So well, residue method is way better than the previous. Okay. Just a couple more exercises. This time, I have two different singularities, and C is a circle of radius 1, centered at 2, and always, as always, this guy is positively oriented. Okay, so I need a visual assistant. So let me draw the picture of this. I have one singularity for this well over here, and another singularity at this point, and well, this is my circle of radius 1 and positively oriented. Okay, so in order to evaluate this integral, then I will need to find a Lorentz expansion of this integrand function, but not about this point, but about that point, right? Okay, so this guy goes this to the fifth is z minus 2 to the fifth goes here, and I will need to somehow manipulate this guy 1/z, but I say this is 2 plus z minus 2, and I'll change this a little bit. So this 2 goes here, and this is 1 plus 2 and z minus 2/2, just like this. Okay, then now I can use the geometric series. So this guy carries over, and the second guy is this is from n0 to infinity. Since this sign is positive, not negative, so I will need a alternating factor, 1 minus 1 to the nth over here, and z minus 2 to the n. Everything by n. And this is true for when z minus 2, well, this is true when this guy is between 0 and 1. But in other words, this expansion is true for in this analysis from 0 to 2. Okay. Okay, then so 0 to infinity, so minus 1 to the nth, and this is what, 2 n plus 1, because I'm combining this with this, and times z minus 2 n minus 5. Okay. Okay. So now, what do you think is my residue over here? The residue here is so I get residue when n equals to well, I get the residue when n equals to 4, I think. Yeah, if I plug in n equals to 4, then, well, this guy should be z minus 2 to the minus 1, minus first power. Yeah, good, good. So minus 1 and 2 n plus 1, and n is 4. So this is, what is this? 1 over 32, I think. Yeah. Okay, so therefore, the integral of this guy is just 2 pi I times the residue, which is pi I over 16. Okay, okay, good. All right, okay, good. Oh, you should always be cautious when you try to find the Lorentz expansion of your integrand function. I mean, you always should find the right Lorentz series in order to find the residue. So, well, that means, well, here I am actually finding the Lorentz series of this guy, but, well, you can also find the Lorentz series about this point when your annulus is between when your annulus is between 2 to infinity. I mean, so like this. Z minus 2 goes to here, and, well, you know, I can always choose this guy to be Z minus 2 and Z minus 2. So is it right? Am I right? Yeah, so this Z minus 2. Okay, yeah. Okay. Then this is 1 over Z minus 2 to the 6, and 0 to infinity minus 1 and 2n over Z minus 2 to the n. Well, just consider this Lorentz expansion of this guy, your function. Then, according to this expansion, the first coefficient of the negative power of my Lorentz series, well, in this case, the least negative power of this expansion is starting from what? Z minus 2 raised to the negative 6. So therefore, according to the expansion, the first coefficient of this expansion equals to 0. But you should not be calling your residue equals to 0, right? Because, well, as I mentioned earlier, then, well, this is not a right expansion just to get the Lorentz, just to get the right principal part of your function around the point, right? Why? Because the inner radius of this expansion is not 0. You know what? The inner radius of this expansion equals to 2, right? I mean, because, okay, so when you're getting this out of here, then you always need to make sure that this guy should be between is less than 1. But in other words, this is okay. Oh, so that means this expansion is true for this region. And so, but therefore, since this number is not 0, so we cannot say this is the principal part. So you can never be able to find any principal part from this expansion. Okay. So don't be confused. Okay. All right. So how is okay? The question is, how do we get? Is there any faster way to compute the residue of any given function? Well, because it feels like in order to get the residue of any function, then first you will need to compute the Laurent expansion of the entire Laurent expansion of your function. All right? But well, actually that is not necessary because well, what you need is just first negative coefficient of the Laurent your expansion. Therefore, you don't need to get the whole Laurent expansion of your function. So just in order to reduce the computation, so I'm going to introduce this nice proposition. Okay, suppose f has an isolated singularity at this point. If Z0 is a simple pole. Do you remember the definition of the simple pole? Yeah, speaking of poles, then well, good. Okay, let me just go back to our previous exercises and try to find the order of the poles here. So here, Z equals to 0 was the singularity. And according to this, then well, the least negative power, starting from Z to the negative third, therefore, I say the 0, the origin is the pole of order 3. Okay. What about this case? Well, here we were talking about the singularity at Z equals to 2. And well, just by looking at this principal part, the least power of Z minus 2 appears when n equals to minus 5, right? So this is the pole of order 5. Okay. So well, I mean, you can always find the pole of your any singularity. Well, if that is a pole, if your singularity is an essential singularity, but there is no such a thing, but as long as well your negative powers of your Laurent expansion is finite, then you can always define a pole of the order of your pole. And this assumption is only true for when Z0 is a simple pole. In this case, the residue at this point of my function is what do you think about this thing? Are you convinced? Yeah, kind of, right? Because, well, so provided that this guy is a simple pole, then the least negative power of this guy, the least negative power of Laurent expansion of this guy should be B1 over Z minus 0, right? And if you multiply everything by Z minus Z0, then there will be no negative powers after you multiply by this factor. And tending Z to the Z0, then you did, and this number should be precisely the B1 of your Laurent expansion, right? So this is how you get the residue of your function, without computing the Laurent expansion itself. Okay, well, maybe I can generalize this idea for any pole of order M. So in general, if this is a whole of order m, then the residue is m minus 1, 1 over m minus 1 factorial times z is tending to z0 and z minus z to the zeros times f of z, and you take a derivative of your function by n minus first times. Yeah, this is now getting more complicated. But well, I can clearly say that this is a nice generalization of statement number 1. Okay, so well, maybe I will need to give you the decent proof of statement number 2. So the proof goes like this. This is not working. Yeah. Oh, okay, good. Okay, so since we are assuming that the point is a whole of order m, so the Laurent expansion of my function is the 1 over z minus z0 raised to the mth power times bm and bm minus 1 so and b1 of z minus z0 plus the analytic part from 0 to infinity, so an z minus z0, so which I'm not that interested. And always don't forget to mention about this analysis. Well, and so now, how do we extract this number from this expansion? Well, first I will multiply everything by z minus z0 to the m's power. Then, well, this is bm plus bm minus 1 times z minus z0 to the first, and b1 times z minus z0 to the m minus first, and plus this guy, but this time this is plus m. Okay. Well, I have this. Now, what if I take differentiation? What if I differentiate this guy m minus first time? So everything is now taken derivative m minus first time. Then, well, and these are all polynomials of orders less the degree whose degree is less than equals to m minus 2. So therefore, by taking m minus first times of this many differentiation, these guys are all vanishes. And so therefore, all we have is just m minus 1 factorial times b1 plus the summation. Well, this is n plus m. Well, bunch of some other numbers. Well, these numbers are not that important. So all the way goes to n plus 2 and an z minus z0 to the n plus first. Okay, so, well, and finally, if I let everything, and so if z is tending to z0, then this guy vanishes, and this, well, so only this guy survives. So take a limit. Should be the n-1 factorial times the residue. Okay, good. So these are some technical lemmas. And I think this is someday this will be useful when you try to find the residue of your function. Okay, what's next? The next theorem is about the Cauchy's residue theorem. So this is especially useful when your curve of integration is enclosing not only single singularity, but if your curve is enclosing finitely many singularities in the region enclosed by your curve C. So the Cauchy's residue theorem, and this is a statement. So I have a simply closed curve, a simply closed curve, and as always with positive orientation. Suppose that my function, my integrand f is analytic. Well, must be analytic on the curve itself, and a region inside of the curve C of the region bounded by C. Well, but not everywhere. Well, we have finitely many singularity on this region bounded by C for a finite number of singularity. I would say zk inside C. Okay. All right. So this is the hypothesis, and the conclusion is, well, the integral of your function around this curve is just nothing but 2 pi times the sum of all residues. So this is the Cauchy's residue theorem. Okay, so what is the proof of this? Well, should not be horribly complicated. But I also want to, first I want to draw the picture of this. I have a complex plane, and I have a curve with positive orientation, and C, and we have a finitely many singularities in the region bounded by this curve, and from Z1 to Zn. Okay, so since we are interested in the integral of my function around this curve, I feel like this is the best time to make use of the Cauchy's integral theorem on multiply connected region. So what is that? Well, just draw a bunch of simply closed curves around each of these singularities, and this is C1, and this is C2, and this is Cn. And let me say all these curves, they are equipped with positive orientation. And because of the Cauchy's integral theorem, the region outside of these red circles and inside of this huge curve C is clearly analytic, right? Because, well, every singular point is now being excluded because, well, we are taking a huge hole around these singularities. So the remaining area, so there is no singularities in this remaining area, right? And therefore, we can use the Cauchy's integral theorem, so which says that this is plus the, the summation of equals to 0, right? But so in other words, the huge integral is nothing but the sum of these small integrals around each of these yellow red curves. And these red curves, the integral about these red curves can be written in terms of the residue zk of my integrand function. Sorry. Okay, good. Okay. All right. It's a no-brainer. Okay, so since we now have the Cauchy's residue theorem, so we can actually think of an integral of a simply closed curve which contains more than one singularities. And z d of z. If I want to consider 4 cases, the curve is z equals to 2, and the second case is z is 1 over 2 and 3, when z minus 1 is 1 over 2, and finally z minus I is 1 over 2. Yeah, drawing a picture will be really helpful in this case. Well, just taking a look of this denominator, I can clearly see there is 2 singularities at the origin and at this point. Okay, and so what do you think is the order of each of these singularities? The order of these poles. Yeah, clearly these are poles, right? And I am pretty sure that the order of this pole should be 1, right? And order of this guy is also must be 1. Okay. All right. So the first curve here, the first curve is when z equals to 2. Sorry. Yeah, I don't want to ruin my picture. Yeah, so forget about this curve. But the first curve is actually enclosing, containing these 2 singularities. And for the number 2, well, we are talking about a curve that only contains this singularity. And for number 3, and this curve is containing just this guy alone. And for number 4, and well, this curve contains no singularity at all, right? Okay, all right. Yeah, so this implies, yeah, I already know answer for case number 4. The equals to 0, right? No brainer. All right, and in order to compute number 1, 2, and 3, I will need to find the residue of each of these singularities. I want to compute the residue. So when z equals to 0, 4 minus 3 times z. I'm going to use this formula that was being introduced in the previous lemma. So just times just z and times. So this is, this is easy computation. Z minus 1, 4 minus 3z. And this is a finite number, which is minus 4. Yeah. Since this is, well, having a finite number from this limit tells us, well, this is, well, being able to get a finite, well-defined number out of this limit gives us the idea why the order of this pole must be 1, right? So, well, if this the pole, if the pole order of this pole was greater than 1, then, well, I may not be able to get any finite number. But since, well, we have a finite number, so therefore, yeah, this guy, the order of this guy is 1. Yeah, I mean, this is a simple pole. And in other words, so when z equals to 1, and so z minus 1 times the function. This is just a level of the high school algebra. So, well, I will not be spending too much time on here. So this is 1. So for case number 1, the answer is 2 pi I times minus 4 plus 1. And for case number 2, this is 2 pi I times, well, minus 4, yeah. And for case number 3, and 2 pi I times, just 2 pi I times 1. And finally, yeah, this guy equals to 0. Okay. Yeah, I know this is getting a little bit tedious, but just allow me to introduce just one more exercise about using the application of the Cauchy's residue theorem. C is a circle centered at the origin with radius 3/2 and positively oriented. Okay. Hold on. Well, I have two clear singularities, +1 and -1, yeah, which is obvious. But well, you know, so tangent is defined to be always sine over cosine. So this function also must have some singularities when cosine equals to 0, right? But well, you know, even if you're working with the complex analysis, the complex cosine function attains 0 if and only if v equals to just pi over 2 plus minus and times pi, right? Okay. So okay, again, picture, yeah. I read because I like it. This is my complex plane. I have two singularities, +1 and -1. And well, also I have another singularity at pi over 2 and minus pi over 2, right? So, and well, and the circle we are talking about here is that has the radius 1.5. So, okay, so what is pi over 2? Which is 1.5, slightly bigger than 1.5. Okay, so yeah. Now this is getting confusing, but I think this is our curve. Okay. Oh, okay, good. So it turns out it only contains two singularities, +1 and -1. Okay. Well, so, and now everything is just a matter of computation. So when z equals to 1, the residue here is, well, in this case here, I am also pretty sure the order of this pole, order of this guy, when z equals to 1, is 1, right? So which is a simple pole. So therefore, z goes to 1 and z minus 1 times and what is this? So this is just tangent 1 over 2, yeah. And for the another singularity, not this, is this is minus 1, so this is plus 1. Okay, so is it? Oh, no, but since we're plugging in z equals to minus 1, yeah, minus. Oh, so they have the same residues, right? Okay. So the answer is is just 2 pi I times 2 times 2 over tangent 1. So 2 pi I times tangent 1. Okay. All right. Okay. Just one more technical lemma that will help us. That will help our computation. Suppose that f is analytic at this point, and also suppose that f has 0 of order m. Okay, so you know what I mean. So if f has a 0 of order m at this point, that means if you're taking the Taylor expansion of your function around the point, then the least positive power should be n, right? Well, in this case, the reciprocal of the function 1 over f of z has a whole of order m at this point. Okay, so how do I know that? Well, not a big deal. Well, yeah, I think this is kind of obvious to me because, well, some function having a pole of order m, if and only if you multiply your function by z minus z0 to the m's power and take a limit, then you're going to get some non-zero number, right? Sorry, just forget it. I'm going to give you the proof, official proof of this. Well, f has a core of order m at some point, then this implies, well, this is what we actually did in my previous lecture. You multiply your function by z minus z0 to the m's power, and this guy exists, and this is non-zero. Okay, so therefore, well, because our assumption says that f has a 0 of order m at this point, so around when z is very close to the point z0, then you should expect this kind of Taylor expansion. So a0 and a1, z minus z0 and da da da. And more importantly, this guy should be non-zero, right? So 1 over f of z times this guy is tending to 1 over a0, which is none. Okay, yeah. As z is tending to z0. So, well, since I was able to get some non-zero number from this limit, so that this means this guy has a pole of order n. Okay. Another proposition. I have a function which is defined by quotient of two functions p and q, and we suppose that q has a simple pole. Sorry, not simple pole. So it has the simple zero at this point, and p of z0 is non-zero. Okay, so well, that means f of this is non-zero, and so p of z0 is non-zero, and q of z has a simple zero. This implies that this guy has a simple pole at this point, right? F of z has a simple pole at this point, and the residue at this point is p of z0 by q prime of z0. Okay. Well, this is not, well, at least at this point, so this last statement is not that clear to me. So, well, it requires a little proof. Well, okay, we consider a small annulus, and we are assuming that q of z has a 0 of order 1. So a1 plus z minus z0, a square, a2, and da da da. And and since this is actually the Taylor series of a function, so this is, well, actually f prime of z0 by 1. Yeah, so yeah, I don't need to use a denominator. Yeah, so this is actually, this is not f, sorry. I'm confused. Yeah, this is q, okay? Yeah. Okay, now everything makes sense. So residue. Well, so I'm pretty sure that this guy has a simple pole at this point. So in order to get the residue, I will need to evaluate this limit, z minus z0 times p of z over q of z. So this z minus z0 is now being canceled to each of these z0s, z minus z0s in the denominator. So this is going to be just p of z times a1 plus z minus z0, a2 plus da da da. So p of z0 by a1. But you know what? Well, you know what? But a1, we already know that a1 equals to q prime of z0. Okay, so this proves the statement. All right. Just one more computation. Z to the fourth minus 16 and plus Z times e to the pi over Z and everything dz, and this here the curve is not, well, this time this is not a circle, but say this is an ellipse, y squared over 9 is 1. Okay, hold on. So, well, this integrand function has, well, this integrand is now getting more and more interesting. Well, if you factor out this, well, I can actually locate 4 singularities in the first term of this integrand, which is plus 2 n minus 2 and 2 times I and minus 2 times I, right? I have 4 singularities, and the orders of each of these singularities should be just 1. They are all simple poles, right? But the problem is different for the second term. Well, e to the not pi z, but e to the not pi over z. So therefore, well, I can expect another singularity at 0, but this time around, this is not a pole. This is an essential singularity, right? Do you remember this? Okay, good. But even if my singularity is an essential singularity, but I should be able to make use of the residue integration. Still, okay, so the plus or minus 2 times, well, oh, sorry. So, okay, so, but yeah, first, yeah, as always, I will draw a picture. And this is an ellipse. This is my ellipse, whose minor axis is 1 and major axis is 3. And I have this is essential singularity. And this is 2, and this is minus 2. And this is 2 times I, and this is minus 2 times I. So this means I don't need to consider these 2 singularities, okay? Okay, so now, so I want to find the residues at these 2 singularities. Okay, so I'm gonna consider 2 plus or minus of zi multiplied by, well, pi z and z minus, not fine, z to the fourth minus 16. Well, this is simple computation. This guy tends to a non-zero number. So this implies this function has simple poles at plus minus 2 times I. And well, maybe since we already introduced this proposition, so let me try to use it. Well, this function is defined by quotient of 2 analytic functions, and clearly, well, this guy, the residue of this guy, well, this denominator itself is an analytic function, and it has a simple 0 at plus minus 2 times I. So residue at 2i of this function and z to the fourth minus 16. This is, well, according to this proposition, the residue at this point can be simply evaluation of the numerator at this point by the derivative, the evaluation of the derivative at this point. So 2i times e to the 2 pi times I guess. And well, if you take a derivative, this is just 4 times the third, right? So which is just 4 times 2i to the third, okay? And now what? So this is, I have 1i here, minus, and this is, well, 2 pi I is just, e to the 2 pi I is just 1. So, and just, this is minus 32 times I, so which is just simply minus 1/16. And likewise, when minus 2 times I, then this is minus 2i times e to the minus 2 pi I over 4 times minus 2i to the third. Well, yeah, so this is, I think this is again 1/16, I guess, minus 1/16, I think. Yeah, good, right. Okay, and for the essential singularities, which is this, this is z to the n factorial, and I should have pi to the n by z to the n. So this is z plus pi square over 2 times z 1/z and da. So well, so this implies that this should be our residue, right? So v times e to the pi over z is just pi square over 2. So therefore, all you need to do is just take a sum of these 3 residues and you multiply by 2 pi I, and that is going to give you the integration, okay? Times minus 1/16 minus 1/16 plus pi square over 2. Okay, good. Finally, I want to talk about the residue at infinity. Okay, so, well, we consider this scenario. Suppose that f is analytic on some curve and region bounded by a simply closed curve. Except for finitely many. So I have a curve here, and this guy is now positively oriented, and it contains some isolated singularities from Z1 to ZK. Well, in this case, well, there is some large number, large positive number. This is the center, and this radius is R1, such that F is analytic on this outside radius. So outside of this region. So well, outside of the region, which is outside of this circle, large circle. Okay. 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 So now things are getting a little bit interesting. I'm gonna take, well, yeah. Yeah, I'm running out of space, sorry. Yeah. Okay. Now, what I want to do is I want to choose another circle around here. And let me say this radius is R0. So, a positive number. R0 is greater than R1. And we consider a circle whose radius is R0. But this time around, this guy is not positively, but negatively oriented. Okay, so. Okay, why is it negatively oriented? So in order to explain this, I will need to go back to the notion of the extended complex plane. So it goes like this. Well, extended complex plane is now considered as a two-dimensional sphere. And the south pole is considered to be the 0. So this is now our 0. And so this is, well, topologically, this is the same as S2 minus the south pole. And this north pole should be also understood as, this is sometimes we call the point at infinity. This is Z coordinate, and this is W coordinate. And this guy, this point at infinity is now being mapped to the origin of another complex plane. But this complex plane is now C2, this is now S2 minus, topologically, the north pole. Well, and we have two different coordinates, and which is the Z, and this another one is W. And there is a rule of coordinate transformation. So, which is simply Z equals to 1 over W. So, so this means, well, suppose then I have some function, which is now, okay, all right, if my function, which is defined on this Z plane, so this is the plane that where we usually working on. And suppose that my function has a simple 0 at this point, right? And this point B should be identified to the point somewhere around here. But from the viewpoint from the W plane, the simple 0 at this point should be now understood as the simple pole on the W plane, right? And well, And also in this case, my function here, f, is considered to be analytic outside of this large circle. And this is from the viewpoint from the z plane, this guy is now negatively oriented. So this is what? This is a, and this large circle should be identified to a circle somewhere around here, right? And since, well, even though this guy is negatively oriented from the viewpoint of the z plane, but however, from the viewpoint from the w plane, this plane is, this negatively oriented guy is now positively oriented, right? From the viewpoint of the w plane, okay? So, from the viewpoint of w plane, the curve, the C0, is positively oriented. No. Okay. So, and this is possibly oriented. Yeah, I know. I just realized that I just ran out of time, but just give me just one more minute. And we are assuming that this my function f of z is analytic and outside of this large, well, outside of this circle. So this implies this is my circle C0, which is negatively oriented, but this circle is now positively oriented. And my function f is assumed to be analytic at this point. This implies from the viewpoint of from the w plane, that means my function is now analytic on this region, right? But well, but be careful. So being analytic on this region, being analytic on this region does not imply my function is also analytic at this point, right? Because every z is now being replaced, should be replaced by 1 over w. So therefore, being analytic everywhere outside of this region implies that my function must be must have some non-singular, isolated singular point on this point of infinity. Okay, yeah. Thank you for your patience, and I'll see you next time.